Okay, in activity 12C, what we're going to look at is a topic called apportionment. And what that is a situation where you have a select amount of items that you have to divide up proportionally to another set of groups. The example that they give, and I know that they'll kind of come back to later on here, is about the House of Representatives. In the House of Representatives, you have 435 seats, and you want to divide those 435 seats to the different states. But the states have different populations, like California and Texas are going to be higher populations than, what are some of them that don't have much? Probably Iowa doesn't really have like a heavy population. Rhode Island, very small. So those 435 seats, what you can't do is just divide them up amongst the 50 states, which is I'm going to show right down here. You can't divide it up amongst the 50 states because then you're going to say, all right, every one of the states is going to get 8.7 seats. Well, that's not fair to the states that have higher populations. In addition, the other problem that we get is this concept of a decimal and like how you're going to deal with that part of it. Okay, so then what we do is we look at maybe taking like the whole population and even dividing the whole population by the number of seats, and then wanting to give those amount of seats appropriately in the population. So like the states like Texas and California get a little bit more. But even when you do that, you're going to end up with some decimals, and ultimately that's what this whole activity is about, is when we divide up those seats, how do we do it so we don't end up with decimal amounts? You can't give half of a seat to a state. How do we do that to avoid losing the decimals, but also to make sure everything sounds fair? And even like that, when it's described, seems like a real simple idea would be to just round in a certain direction. But we're going to find out in this next portion here that even when you're doing the rounding, it might not add up appropriately. Okay, so this part here just gives you a little bit of background on the House of Representatives. That, it said above that, 435 seats, and you're going to divide those seats based on the population. You're also going to make sure that every state has a minimum of one representative. That being that. I don't think that comes up in anything that we're going to do in the activity, so I wouldn't quite stress that part there. Okay, so now we're going to look a little bit closer at, I think it's Texas. Yeah, we're going to look a little bit closer at Texas and see how many seats that state should get, our state should get, and maybe a little bit of the pitfalls in that at the end. Okay, so a couple things first to define at the beginning. We have something that's called a standard divisor. We also have something called the standard quota. Okay, the standard divisor is the average number of people represented per seat. So that's going to get calculated by taking the population that we have in the U.S. and dividing it by the number of seats that we would have in the U.S. Okay, so the U.S. population in 2010 was 309. So this is a little dated, but the concept is still what we want to do. So you have 309 million people. You're going to divide that by the total number of seats that we have available for the country, which would be the 435, and you'll see the calculation over here. That divides that and gives you that number. And I think it actually did turn out to be a whole number. If I'm wrong on that, then, actually it says round to the nearest whole number. So maybe my calculator went ahead and did that for me. But you're going to get that number, the 710, 345. Okay, the standard quota for a state is the number of seats that would be entitled if we did fractional seats and all that stuff, which we're going to address and how to deal with that. So for that, you're now going to take the state population and you're going to divide it by the standard quota. Okay, so Texas population is going to be the 25 million, etc. You divide that by the standard divisor and you're going to get this number, the 35.3, and a bunch of higher digits from there. So we do want to round to the nearest 10th. I thought it was necessary to show you that number because when it does round to the nearest 10th, it's going to start looking somewhat different. So you get the 35.4, but that would... Okay, so conveniently, the top of the next page actually gives you the answer to the page on the other side, which I really think is a cool idea, and worksheets turn out that way. So you know your answer is the 34.4. Okay, but we think about what that means. That means that of the 435 seats that are available, 35.4 of those seats should go to Texas. But a seat is a person, right? Well, a person's going to sit in that seat and represent that state. So the big question is, what do we do with the 0.4? Okay, now one option is that you just do the regular rounding that you would for any type of number, and that being a 0.4 is going to round down to 35. However, here's the truth of the matter. It ended up that the 35.4 turned into 36. That Texas didn't lose that 0.4 of a seat, but they actually gained that 0.6 of it and taking you all the way up to 36. So they got to keep that part, and then some other state, I guess, would have lost a little bit of their decimal value. So why does that happen? And it's an unusual thing because in our mind we're thinking rounding is the best way to do it. The problem is that when you round the 50 different times that you have to round for all of the states, that sometimes you might end up rounding down more than you end up rounding up. Like there's not a balancing act, and then somehow we end up with an unfair, or not an unfair, but you end up with the wrong number of seats in the end here. And that's what we're going to look at here in this little first case study. And what I believe that we do is this. So I'm doing the notes just partially as I record them, just so you know. This case study, this real simple version of it, we're going to look at it's not unfair, how it doesn't work out based on just general rounding. And then we're going to go through these different methods that were listed just above, which I hadn't mentioned yet, the Hamilton's method, Jefferson's, Webster's, and the Hill-Huntington method. Those are different ways that we can deal with this inconsistency in the numbers. That's the word I was looking for. Okay, too high up there. Okay, so we have a fictional country that's got 10,000 people in it. You've got 4 states, and we're going to do 100 legislative seats. So obviously these numbers are set up to make the numbers look a little bit easier. In my personal opinion, I actually think they make things difficult to really to understand later on, but the math turns out nice with them. Okay, as mentioned at the beginning with our country in Texas, we need to come up with a standard divisor. That's always the very beginning of this, and that's going to be taking your total population and dividing by the total number of seats. Okay, and that's something you're going to do in every single example that we talk about apportionment. You're going to take the total population and divide it by the number of seats. So we take 10,000, we divide it by 100, we end up with 100. That is your standard divisor. We're now going to be using that. I'd like to draw an arrow here, but it'll mess up how everything looks. That's going to go down here when we start figuring out your standard quota. Okay, and usually after you do this part, you transition into a table set up for information. Here's our 4 states. Here's the populations that go with each one. Obviously, we don't want to do this with America because then you would have 50 of these columns. So you only got 4 states here. These are their populations, a nice variety of those. You're going to take those and you're going to divide them by the standard divisor. Makes sense, right? Because it's called the divisor. Okay, now here's the conveniency of all the division and the math with that 100, is that when you divide these numbers by 100, you're really just moving the decimal over 2 spots and you get all of these numbers, right? Decimal goes over 2 spots, 37.35. Okay, and then next, based on how we've been taught math in the past, because you can't have a partial seat, we're going to do some rounding. Anything that's 0.4 or below is going to go down. Anything that's a 0.5 or above goes up. So this one's going to round down to 9. The 27.26 is going to round down. That's definitely going to round down with the 0.0. That's also going to round down. So notice we never rounded up at any point. We didn't. And now if you add all these numbers up together, because we never rounded up at any moment in this, you actually end up with 1 seat less. We're supposed to have 100 seats. And if you add up all of these numbers, you get 100 because that's your total. That'd be the total number of seats. And then this is the actual number of seats that we end up with here. So we're off by 1. And then the answer to this is going to be no. If we just do the regular standard rules of rounding, does it work out? It doesn't. In some cases it will, in others it's not going to, and I guess most often it won't. Okay, so then what's going to happen in the next parts? We're going to go through these different methods. Each is a little bit different. A couple of them I believe are pretty confusing, but each of these are going to be methods and how we can deal with that inconsistency in the number of seats, like how we can figure out who gets that last seat. They all get at least that much, but who's going to get the extra seat, and how do we really discuss the fairness in that? Okay, next what we're going to look at is Hamilton's method. Remember, the goal in this part and all the remaining parts is to figure out how to take those extra seats and give them to the appropriate group. That should get them. Okay, the beginning part of this is all the same thing that you would have done beforehand. You have your standard divisor. You're also going to create a standard quota. But then we introduce this new thing here, which is a minimum quota. The minimum quota is basically whatever number you get after the standard quota, but by rounding it down. Okay, so there's a whole value and then there's a decimal part, and when you round it down, you're guaranteed to give the whole value number of seats to a state, that they're not going to go less than that. And then what's going to happen is all the decimal parts of that sort of go into a pool, and we figure out how to deal with those. So let me go down to the table that you would begin with. Again, this is Hamilton's method. What did we divide? We divided the 10,000 by the 100 seats, and we know that we should be, then I don't know where I'm pointing all this, but here's your standard divisor. I know we did the division. You got that standard divisor, and you're going to take the population and you're going to divide it, and you got all of these numbers, which you saw before. So then the minimum quota, this is the new thing here. The minimum quota is going to be rounding all of these down. So every state's guaranteed that number of seats, which should look like what you saw in the example at the beginning anyway. Not that it's always going to be the same, because in that example, they all rounded down anyway. But when it adds up, you only end up with 99. So that means that you are short one seat. And then you don't normally have to create this row. I think you can keep track of it here, but you're going to take all the decimal portions of it, right? What we're doing is just kind of separating that from the whole value so you can see them. And if you add all those up together, it should add up to 1, which is that one seat that we're missing. Okay, and then next what you're going to do with Hamilton's method, here it is in part D, you're going to look at all those decimals, and whoever has the highest decimal is going to gain a seat. They're going to get 1. If you have more than 1 seat that you need to give out, maybe you've got an offset by 2, which is totally possible, what you'll then do is give the highest decimal a seat, and then you're going to give the next highest one a seat, and then so on. You would continue that process until all the extra seats have been given up. You should not end up in a position where everybody's going to receive a seat and then you got extras, because all that would have happened in the original division parts of this. So you're not going to see too many seats needing to get given out. Okay, so if you look at all the decimals that we have here, the 0.36 is going to be the highest by just a bit over what state D has here, 0.35. So state A is going to be the one who gains 1, so I just wrote in the corner there. They're going to get an extra seat, which is going to move them from 9 to 10, and then everybody else will just stay the same. And if you add all that up, you're going to get to 100. All right, next what we're going to look at is this thing called the Alabama paradox, and that's when by adding, well, it says it right here, by adding extra seats, there's this chance that what happened from beforehand to the new setup, so having more seats in there, that actually a state loses a seat. Because you think that if you add in extra seats, that like somebody's going to gain more, the others might stay the same, but it's actually possible that that you lose one in the whole process. It doesn't mean that it's wrong. It just means that it happens. Okay, so just so that you can see like when this happens, more importantly, what I think you're going to take out of this is just seeing another example of Hamilton's method. That's the real thing that I'd like you to take from here. Okay, so we're going to switch to 101 seats, just add 1. And you would think that, okay, well, we're just going to add that seat to one person, and it would probably go to state D because they were the next in line to gain 1 anyway. And you'll see something unusual actually happens in this case. All right, standard divisor, you're still taking your population, you're dividing it by the number of seats, and you end up with this kind of goofy looking number, 99.0099. You might notice all the little smudges here because apparently I don't know how to divide things correctly several times in a row. But the good news is that the activity shares all these numbers with you, So that helps me catch any mistakes I might make. Okay, so I took all my populations, I divided them by the divisor, and I wrote down these numbers. I put them in that spot because that's where I had space. You're then going to go with the minimum quota, which means just take the whole value part of this thing and write it down. We then have this row, which again I said might not be totally necessary, but this is all of your decimal numbers. In this case, they're going to actually add up to a total of 2, because when you add up your minimum quotas, you only ended up with 99 from there. So there's a whole bunch of extra decimals that add up to what is more than 1 this time. Actually gives you 2. Okay, so now we got to figure out how to divide those up. According to Hamilton's method, what we're going to do is look at the decimals and then give to the highest ones. And we got to do this 2 times. So that decimal is the highest one. So I wrote down here that they're going to gain 1 of my seats. So then I don't look at that one anymore. As a comparison of these, state B is going to have the next highest decimal, 0.53, so they're going to gain 1 seat. Okay, so 9 stays 9. The 27, I'm going to gain 1 and get to 28. 26 will stay 26. 37 is going to gain 1 and become 38. And then everything adds up to 101, which is kind of obvious because you got all your minimums. Actually, you had all your minimums plus those 2 extra ones that got added in, so it should work. Okay, and then, so that's really just an example of Hamilton's method. But in addition, we get to talk about this thing called the Alabama paradox, which said that when we added in that extra seat, that it was possible for a state to have lost one from what they previously had. So maybe last year with 100, where's that page? Okay, when we had 100 seats, state A had 10, there's 27, 26, and 37. So they had actually gained that one. They were ended up at 10. But when we added in that 1 seat, state A actually didn't gain that one that they used to have. So they went back down to their minimum at 9, and it was the other 2 that got it. So from one year to the next, when you added states, you actually see somebody kind of missing out on that extra one there. Up next is Jefferson's method. And this one's going to be a little bit confusing on how they come up with the numbers, but I guess I'll touch on that once we get to those parts. The beginning of everything is still the same. You're still going to have a certain number of seats, and you're also going to have a population, and you're going to want to divide those to get a standard divisor. The second thing that you're going to do is divide the state populations by that divisor to go what's called that standard quota. Okay, let me just go ahead and go down to the table, and I'll just talk through all the different steps as we go through it. Okay, the divisor again. The divisor was a 100. I know that it is, but okay. So the divisor was the 100, and we don't show that step now here with the actual divisions not written out, but they did do it. They took the population and they divided by the 100, and then that's how we got all of these numbers that you're used to seeing. The minimum quota, we're still going to look at that with Jefferson's model. We're going to take out Jefferson's method, is actually called. We're going to take out the decimals and then just drop it down to the whole value numbers there. And then when this adds up, you're going to see you get 99. So we're still off by that seat. None of that has changed for our sample 4-state system that we've got right now. Okay, but instead of looking at those decimals and giving a comparison and then reallocating the seats to those, what we're going to do is use a modified quota. We're going to find a modified quota by using a new divisor. In this case, they're going to do a divisor 99. So up here it mentions that what you're going to do, like if it doesn't work out well, if everything is not, if all the seats aren't accounted for with the minimum quotas, then what we're going to do is choose a smaller number to divide by, something smaller than the standard divisor. So our standard divisor was 100, so we're going to drop it down to 99. The idea with this is, if you can imagine this with numbers, if you divide a set number, like a population, if you divide it by something smaller, the return is going to be something bigger. So by dividing by the 99 instead of 100, those values are going to turn out larger than what they used to be. And the hope is that when you divide by something smaller, and you get bigger numbers back, so that 0.36 is now 0.45, we're hoping that at some point, one of these is going to collect an extra like state in their minimum quota then. Okay, so we divide by the 99 and we get this. We divide by the 99 and get all the way down the line there. And now if we do our minimum quotas, you still have the 9, you still have the 27, the 26, and 37. Nothing actually changed. You didn't actually see any difference in here, so we're still at 99. Did not meet what we wanted to there. So then we try something else smaller. We're gonna go with 98. Okay, so we divide by 98, we now get 9.55, we get the 27.81, and so on. Okay, now take the whole numbers, take the 9, you're gonna take the 27, you're gonna take the 26, and you're gonna take a 38. But this is the spot where you notice a change. It used to be 37. Up here was 37. After using a 99, it's still 37, but then using the 98, this one is actually giving us back a number that has moved up into the next next amount. I guess the decimal carried over into the next number, so now we're at 38. So your final apportionment, it's these numbers. There's not really any reason to rewrite them, but I'll go ahead and do it. You can see that one increased up to the 38, and now we're at 100 seats. Okay, so in this case, D ended up gaining where, like originally, I think it was state A got that one. Okay, so what we're going to see in the next table here is basically practicing Jefferson's method one more time. That is what I'd probably say is the main takeaway from all of this stuff. But there is this other little detail that we want to address, sort of like in the previous part we talked about the Alabama paradox. What we're going to talk about is the quota criterion. I hope I said that right. Okay, when you do your standard quota, remember way back at the beginning we did Texas and got 35.4. Whatever that standard quota is, that state should get either 35, which is rounding down, or 36 seats, which is rounding up. We shouldn't see all of a sudden that, okay, Texas used to be 35.4, and then they walk away with 34. They walk away with something less than rounding down. They also shouldn't walk away with more than rounding up, like 37. That shouldn't occur. But we're going to see that that actually happens when we do it in this case. All right. Oh yeah, I want to make sure I noted that. This is a new state scenario. We finally got some new values, but it's still 4 states, but they're going to be new numbers, so you're going to see all the populations changed up on you. We still have the 10,000, but we've just kind of moved the numbers around to give a different setup and make it work for this problem. Okay, your divisor is still going to be 100 because you had 100 seats dividing into the 10,000. 10,000 divided by 100 is 100. That's why I said the numbers might be a little confusing, but they work out for the math, I guess. Okay, so right here, when you divide by 100, you can just move that decimal over, so you get all of these numbers, which of course still adds up to 100. We're going to take our minimum quotas, just drop off all the decimals, and when you add it up, you end up at 97. Okay, we actually end up fairly short from what. Actually, I don't think I added that up correctly. Let's double check. It should be 97. Six plus 16 plus 10 plus 65. No, it isn't 97. Okay, I'll assume that I did it right, and let's see then what goes on here. Okay, so we're gonna jump all the way to like using 98 and divide by that number, and you're gonna get 6.94, so your minimum quota is 6. You can get 16.59, so your minimum quota is 16. You can divide, you're gonna get 11.17, so this one's changing now, and you're gonna get a minimum quota of 11. Over here, when you divide, you're gonna end up at 67.34, which is gonna bring you up to 67. So that one's also increased. I guess this part will probably make sense in a moment. I'll highlight here. But it used to be 10, so now it's like it's going up by 1. We're not adding 1 onto it, it's just doing that on its own. what was over at 65 is now going up by 2 of them. So that's kind of interesting that they didn't gain 1 seat, but they actually ended up gaining 2. And now your final apportionment is going to be 6, 16, 11, 67, all the same numbers that you just saw right there. But going back to talking about that criterion here, we do have a violation of it with state D. State D actually ended up gaining 2 seats, which is going to take you past its rounding point. So originally it was at 65.99. It was basically 66. But the rule should be is they either drop all the way down to 65 or you can round it just up to 66, but we ended up at 67. All right, next what we're going to talk about is Webster's method. Not that one. What we're going to do is start with a new state setup here. I guess the numbers are going to work out a little bit better if we use these newly created ones. So we got a new set of numbers. These are our state populations. It does still have a total of the 10,000. So we just wanted to move things around so that the numbers do what we want them to do for the example. Your standard divisor is still 100 because we had 100 seats that were getting divided into the 10,000 population. So then you're going to divide each of the populations by that divisor. So again, that is consistent throughout all the examples that we're going to see. They divide out and you get all of these numbers. The minimum quota, so here that's still the same. You're still going to drop it down to the number, the whole value. So you get 9, 7, 6, 76, which adds up to 98. So we're off by 2. Okay, and then what's going to happen is you're going to choose a modified divisor. So then you get what we call that modified quota, and for this case they're using 99.85. So right now would be a good point to mention that you don't have to use modified divisors or different divisors that are whole numbers. You can choose something that's different. And with that said, how we choose these numbers, you don't know. You just do a little bit at a time until what we want to happen in the numbers, it occurs. So you're not going to need to worry about coming up with these numbers, just so that you know. Okay, so if we take our modified quota that somebody's figured out will work, and we divide this up, you're going to get these numbers here. All right, over here, and that's 499. I erased it a couple times because I didn't know what I wanted to actually show you. Let me add that one in there. That number does on its own round up to 6.5, but it's going to be important that you don't round like over here to mod. It gets a little unusual, but that number is actually less than 6.5, because what we're going to do in the next part for Webster's method is we're going to take that number and we're going to then decide if it should be rounded up to the nearest whole number or lower down. Right, so over here, again, this is an example that if you were going to round this off on your own, you might call it 9.5. But then the next step is going to be rounding that number up to the nearest whole number. So you want to be careful that you don't round your decimals and then use something that's going to like change the rounding of the whole value. So that one is going to round down to 9. This one was 7.5 something or another. So that guy's going to round up to 8, but this was not 6.5, is actually 6.49, like what we see here. So that's going to round down as well to the 6, and then this one, that 6 is going to round it up to 77, and those numbers will then add up to 100. Okay, and that is also your final apportionment. All right, one more time here. These numbers that you're using to divide by are going to be chosen for you. You're not going to have to worry about identifying those. So there could have been, a process of like checking several different divisors until they finally got to one that works out, and that's what we wanted to share with you there. Okay, for our final method, we're going to look at the Hill-Huntington method. For this, you're going to be doing a brand new calculation, or what I think might be a brand new calculation to you, and when we get to that, just kind of embrace it. Don't think too hard about it, just do what the calculations say, and this is kind of what it is here. It's called the geometric mean, and mean refers to averaging some numbers here. The way that you're used to averaging two things, like an x and a y value, is to add them together and divide by 2. So kind of think about that. Imagine some numbers that you would add and then divide by 2, and it gives you the mean or the average. There's something else called the geometric mean, and it does give you like a good representation of like a middle of numbers, but not always directly right between the numbers. What you do in that is you multiply the two things that you're trying to find the mean of, and then you square root it. So it's almost like you're squaring a number, multiplying by itself, but then you're undoing that part with the square rooting. But they're actually going to be different numbers on when you do that. For example, right here we've got, you're going to end up with these decimal numbers at some point. And I'll show you all this in the table, but you're going to get to these decimal numbers in a calculation, and what we want to do is come up with a good representation of what that number will be. So then what we're going to do is we're going to do something called the geometric mean, and we're going to compare that to the decimal number that we have there. Okay, so this would normally either round down, as we've seen today, which will take you down to 9, or it's going to round up, which is going to be the 10. So instead of taking those two numbers and then like doing general averaging, which would have given you a 9.5, instead of doing that, you're going to multiply the numbers to get 90, and then you're going to take the square root of 90, which is 9.486, etc. They're a bunch of large numbers, so I don't want to worry about rounding them. Okay, and then that is fairly close to this number, just slightly different, and we're going to see a comparison between these and the table part of it. But that is how to do geometric mean. You take two numbers that you want. In normal mathematics, they don't have to be numbers that are one after another, but that's what we'll see here, and you multiply those and you square root them. Okay, so here's the table for Hill-Huntington method. The beginning parts are all kind of the same as what we've done before. You've got state populations, you have a total number of seats, so we still had that 10,000. So that 10,000 population divided by 100 seats, and you got 100. So again, that's our divisor here, the 100. Here's your populations that we've divided, and then you take your minimum quota by just rounding down everything and adding it up, and you find out that you're 98, which is 2 seats short. We then introduce a different divisor. In this case, the divisor went up, and to be honest with you, I don't have a good reason on why they actually did that. The other case, when you divide by something smaller, and the way to adjust the number seems to make sense in how you're going to get to that new seat. So I'm not really sure on why that number is greater than 100. And if anything comes to mind by the time we meet in class, then we can bring that up, but I don't really know right now. Okay, so anyway, that number was chosen for us, and we're going to divide, etc., and you get all of these numbers. Okay, but now instead of trying to round these off or finding your minimum based on these numbers, what we're going to do is calculate a geometric mean. So this is kind of an intermediate step. You're going to take the numbers as if you rounded that down to 9, or if you rounded it up to 10. You're going to take this as if you rounded down to 7 or up to 8. You're going to take this as if you rounded down to 6 or up to 7, and then finally 76 as if you'd rounded down to 76 or rounding up to 77. Those are all going to be the numbers that you multiply, and then those answers you will square root. So this would be the square root of 90, gives you that, and then this is the square root of 56, gives you this number, and so on as you go down the line. Okay, as you look at these, you might notice that, well, I guess I was consistent in taking 3 decimals, but what you want to make sure that you do is you keep enough decimals within those numbers that you can compare them to what was our modified quota, because you're going to see that they get very, very close to each other. Like in this case, you've got obviously the 7, but then you've got a 4, you've got an 8, and then you got to go all the way up to the third number until you see something different, and then that 5 is greater than the 3. Okay, so you'll need to make sure you write down enough. Sometimes that requires you to go all the way to like 4 numbers. Sometimes you only need to go like maybe 1 or 2 decimals. All right, in this part, all of this is going to get us down to our final apportionment. But what we need to do is a comparison between these two things here. We need to compare those. If the modified quota is greater than the geometric mean, then that spot is going to get, or that state's going to get an extra seat. It's going to go up from the minimum quota. If the geometric mean is greater than the minimum quota, it will stay at the minimum sorry, I missaid that. If the geometric mean is greater than the modified quota, then you're gonna keep the minimum quota. You're not gonna add on any seats in that case. So in this example here, the geometric mean 487 is bigger than 474. So that one's not gonna get any extra seats. It's just gonna stay at 9. The next, the geometric, I should always read them this way, the quotient versus the geometric. The quotient 7.485 is bigger than the geometric, so you're going to gain 1 seat, which is going to bring it up to 8. You're taking that larger number, bigger than the 7, right? All right, and the next, the modified quotient 486 is bigger than 480, so you're going to gain a seat here and end up at 7. And the last, the 494 is less than the 498, so you do not gain a seat here. So I think as you go through these, always read the quotient versus the mean. Quotient versus the mean to decide if it's going to go up or if it's going to go down. Okay, so you're keeping the 9 for state A. For state B, it went up to 8. For state C, it goes up to 7, and then we leave it at 76. Those 2 additionals are going to bring it up to the 100.